there are two forces coming against each other when you are choosing this potential. One of them is the ability to fine-tune your interactions so that you can specifically in your simulation alter each and every detail how the agents interact with each other. But then you would have way too many parameters to tune this potential function, which would be the hell of a job to simulate, to tune properly these parameters to adhere to the real life. Interestingly enough, elegantly enough, Morse potential has just two parameters that you can tune, and they are called repulsion and stiffness. In these three examples, I actually tuned the potential function of the red cell, and this cell is actually composed of multiple agents. And when I set the stiffness and repulsion to be high, you can see that the cell, the agents within the cell are not willing to overlap as much at all, which means that the repulsion is big, and they are also stiff, which means that they do not want to change shape. So this can be interesting to simulate some tissue cells. Then you can decrease the repulsion a little, so you allow the agents within the cell to overlap a little bit, which, as you can see, can create a notion that a cell wants to be in some equilibrium when it's not touching anything, in some spheroidal equilibrium. And as soon as it touches something, you can see that it is, let's say, squishy enough that it changes its shape depending on when it touches another cell. And finally, when you decrease both the repulsion and stiffness, yeah, you can see that the integrity of the cell is compromised and it basically separates apart. And yeah, we can question that this is actually something that we would not want to have in our simulation. This would be an artifact that we actually did not tune the potential function properly. And yeah, so here I have some small videos of what we managed to do. So to sum up, when we fit the parameters of potential function good enough, we can unlock quite interesting behaviors, such as we can simulate the cell rhenology, such as on the top right you can see how we can stretch the cell. Or then another experiment here, which was performed by another group, is how the cells interact with each other when they are crossing themselves, crossing each other. And here on these small videos we have the invasions of cells which we made. And yeah, on the right we have our agents in cell to be governed by the Morse potential. So it is somehow able to squish through the more rigid cells. And on the left, we actually use the Kelvin-Voigt potential. And the Kelvin-Voigt potential is equivalent to, you can imagine it as that every neighboring cell is connected to the neighbor by springs. So there is very little movement of the agents. And actually, there is an artifact here which I think should not happen, because as this cell was trying to infiltrate through these rigid cells, it actually folded in half. Yeah, here you can see that it is just a half, so it folded. Let's go next. Yeah, so another quite exciting extension would be that this subcellular element model is capable to simulate organelles. Yeah, so we can either play with the size of the agent. So the cell is composed of agents of different sizes. In this case, we can, for example, simulate a nucleus within the cell. Or we can have different agents inside the cell governed by different potentials, so that we can, for example, model the membrane. or yeah, we can have a combination. Yeah, and I think that by integrating these structures, we can actually study the cellular responses in a more detailed way, that we can almost, we are almost arriving in a middle between the molecular and tissue level simulations, which can be quite interesting. Finally, I picked this one example because I think it's pretty interesting, and it is constrainment ring, cell migrating through a constrainment ring. So this is some real life experimented scenario where a cell needs to stretch its membrane through a smaller constrainment ring. And if the constrainment ring is small enough, you can have some nuclear damage, but yeah, that is not way too important. So we try to simulate it. And here I have a GIF. And there are many things happening here actually. So here you can see that this is a big cell that is trying to squish through this constrainment ring. And yeah, there are many things happening here. So you can see that we are actually modulating also the membrane of a cell, which is in blue. And the cytoplasm, let's say, is in red. And yeah, the cytoplasm is governed by the Morse potential with not big repulsion so that the cells can slightly overlap. And the membrane is governed by the springs so that the membrane's integrity will not be compromised and it will not split apart. Interesting here is that we also needed to somehow simulate that the membrane could stretch. So if you pay big enough attention, you would see that if the agents on the membrane get too far from each other, we actually add one more agent between them so that we can stretch the membrane and let the cell go through. So we actually, there are just very small local interactions here that are converging to some global state of a cell being able to get through the constrainment ring. And I think that this is one of the key ways how to have your agent-based simulator, how to have a powerful agent-based simulator that it is composed of simple local interactions instead of trying to hack your way through or having some global state somewhere and having some global non-localized simulation. Because if you have just simple interactions within agents, you have from the coding perspective, you have much cleaner and simple code, which can be indeed amenable to better high performance computing. Yeah, and it is, while it is always nice to research some new features, none of us will use this feature if it requires supercomputer resources just to simulate a small example. So it is very important to foster collaboration between HPC experts and computational biologists so that we can develop these advancements with HPC availability in mind. And yeah, this can be many things, such as serializing the memory accesses or having reasonable time complexity of the algorithm or good enough arithmetic intensity so it can be adapted to GPU acceleration and so on. Yeah, so designing the models that scale efficiently can leverage high-performance computing so that we can actually use these new features effectively. So again, the interdisciplinarity is very important here. Yeah, but okay, so do we actually need all this? This is the most important question. And I think that it depends on the level of the detail you want, right? If you want to simulate scenarios where we know that the cell shape will not play any major role, we can definitely suffice with cells being represented by simple shapes. Or maybe you will suffice with even more coarse-grained models where the whole cell population is simulated just by some cloud of the probability density. So yeah, you always need to think about what is my way of precision that I need, and maybe that whether this way of precision is really important for my simulation. Okay, so yeah, before we again move to another part, are there any questions?
Oh, hello and thank you. I'm quite wondering about how can you simulate the cell cycle, because there is a stage there like the cell divide its cytoplasm. So how can you simulate this?
So this is a very recent research. We haven't been able to go this far yet. But yeah, the way I am envisioning this would be that we would somehow find the axis of division and then evenly split the agents in the cell along this axis.
Oh, okay. I have another question as well. So, in the beginning of the presentation, you spoke about cancer. So, I'm wondering about heterogeneity. So, I think in your model, it's homogeneous.
Mm-hmm.
It's homogeneous, right?
I think so.
So, cancer is one of the attribute or aspect of the cancer. It's heterogeneity. So, how can you govern this or parameterize this?
So each cell can have its own part of parameters. Actually, PhysiCell simulates you to have different cell types, and each type can adhere to a different set of rules that you define. And yeah, this is, I think, as much as I know how to comment about this. Maybe we can again talk after the presentation and we can, yeah.
Oh, okay, thank you.
No more questions?
Okay, so yeah, let me switch the topic a little bit and talk a little more technical. In the computational and performance scaling of the PhysiCell and digital twins in general. Yeah, so when we are building these digital twins, we face a simple dilemma. We have either more final the detail. We can either simulate more cells and molecules, or simulate finer the detail of a cell by giving a shape to the cell or something else. But the thing is that the finer the detail, the bigger the computational cost. So depending when you scale up or to the side, the scaling is the computational requirements explode exponentially, basically. Yeah, so let's talk specifically agent-based simulations. So they are powerful because, as I said, they can be reduced to a simple different processes, and each process is a well-defined mathematical interaction, which is the ideal target for high-performance computing. But however, even the best compute nodes that you have will eventually hit something that is called the memory wall. So at some point, the performance will stop being limited by your floating point operations and become limited by how fast you can actually move the data from the memory to the core. And this is where the pure computational scaling fails. Throwing just more compute, more CPUs at the problem will not solve it. And to give you more idea, you can have a look at this plot where you can actually see that over the time we are much better at scaling the computational bandwidth than the memory bandwidth. So eventually your code will not be bottlenecked by amount of operations that your CPU can perform per second, but by how many data can be actually moved from memory to your CPU. And for this, we actually distinguish the problems to be like compute bound or memory bound. And more often than not, your algorithm will be actually bound by memory and not by the compute. Yeah, so here I wanted to give you an interesting idea how to have how to look at this sort of a problem. So for this, I borrowed a most recent NVIDIA GPU. And here I wanted to show you the two different bandwidths that this device has, which is the compute bandwidth and the memory bandwidth. So you can see that the compute bandwidth of some specific type, a 4-byte floating point, is 75 teraflops per second, teraflops. And the memory bandwidth is 7.7 terabytes per second. So you can actually see that there is a magnitude of difference between these two things. And we can create this quite interesting metric, which is called ops per byte ratio. And dividing the compute bandwidth by memory bandwidth, we get this thing called ops per byte ratio. And in our case, it is a 10. So this actually means that in order for you to make the GPU busy all the time, you would need to perform 10 different operations per each byte that is transferred from memory to the core. 10 different operations per each transferred byte. So this sounds like quite a lot, right? You can imagine it as you take one number from the memory, and this one number needs to be present in 10 different operations. It's quite crazy, right? And even that is not the case, because here the units are ops per byte, but our flops are not in bytes, but in 4-byte floating points. So we actually need to multiply this by 4. So 10 operation per byte, but 40 operation per floating point number. And now we are getting in quite crazy numbers, right? Each number needs to be in 40 different operations for you to utilize the device, the GPU or CPU, as much as possible. Yeah, so this is why typically your workflow will be memory bottlenecked more often than compute bottlenecked. So how can we actually fight against this? So for this, we can do, from the software side, we can write algorithms that reuse the data as much as possible, or you can do the caching, or you can distribute the problem more effectively, or you can utilize the hardware, the memory hierarchies that you have there. So it can be the caches of a CPU, or the very, very complex memory hierarchy of a GPU, etc. So the thing is, the takeaway message from this slide is that modern HPC nodes are heterogeneous memory systems, and in order to take the most benefit from it, you need to adhere to these memory hierarchies. So in order to give you a concrete example how real is this issue, we actually in one of our projects, we were actually trying to optimize the diffusion problem that I was talking about a few slides before. And on this table, we provide different optimizations of the same diffusion problem. And typically, what you would care about the most would be the second column, the runtime. Yeah, what we care about is the least time it takes for the same process or operation to happen, right? But for the sake of this slide, let's also look at the second column. So yeah, in each row, we were actually creating a new optimization that was mainly related to memory. So we did aggressive data sharing. We minimized the number of trips to the main memory. We divided some domain in a more complex way. you can see that at some point, we almost doubled the number of operations that we needed to perform. But still, the runtime was slower and slower. And this is the case because we were actually bottlenecked by the memory at some point. And with some optimization, we removed this bottleneck. But the CPU was not completely compute saturated. So the saturation of the compute could get higher. Yeah, so this is an interesting example where actually computing more can result in the less overall runtime. Yeah, and this is another example of optimizing the diffusion. And here, the most important thing is that we tried to do the MPI optimization. And indeed, it is quite a complex problem. In order to find the optimal optimization, you need to do a lot of research, a lot of benchmarking. And in this case, if you want to simulate a level of, for example, the whole organ, such as a liver, you definitely need to have multiple nodes. You need to use the whole cluster just for the sake of so many memory that is needed to do the simulation. Okay, so another point of view how to look at optimizations in general is to ask ourselves the question: do we actually need to solve, in our case, the diffusion in this exact way? Could we use some other algorithm? So here we have like two sides of the coin. On one side, we have the domain expert, the bioinformatician that just wants to solve this problem of diffusion. On the other side, we have the HPC expert who just looks at the code and wants to try to optimize the code as much as possible. But if we were to bridge this gap and let these two different experts communicate with each other, we could, for example, exploit or employ the HPC methodology in the choice of the algorithm to solve that problem. So yeah, this is just another case of why interdisciplinary collaboration is so important. Okay, maybe time for questions again. Or I can just continue. So finally, I would like to switch a topic one last time and talk a little more about the AI. Yeah, so today the AI landscape is extremely rich and also quite fragmented. We have domain-specific language models, generative AI, AI agents, molecular AI, synthetic data generation, a lot of stuff. And for scientific computing, this raises a question like, do we need to integrate AI in a way that it would complement our mechanistic models or even replace them? So one concrete area where AI can already play a role is synthetic data generation. So yeah, imagine that in biomedicine, and access to high quality data can be often limited by many factors such as cost, privacy, or even the sheer small amount of the data. So generative models, what can actually do is that they can learn this latent representation of, for example, real omics data and produce realistic synthetic data sets that can preserve the real structure of the data. So you can have more data to exploit, to learn from, and to train on. And this brings me to the AI agents, which I believe is like the most promising integrator of AI and digital twins. So AI agents are, well, they're autonomous. They can perceive the environment. They can somehow interact with the environment, do some reason about the goals, and take some actions. So in this context, we can actually envision some therapeutic agents built on top of the frameworks. Yeah, in this paper, there are actually the whole agent laboratory, where each agents this is a different person in the laboratory, and these agents can communicate and combine together. And this is not a wild concept, as we see in, over the time how the technology matures. Yeah, we can see these rack pipelines or deep research that has been already employed by NVIDIA and other big players. So this indeed makes sense to have in your pipeline different LLM models, different AI agents, where each have different role, each have different context. So overall, they can give you some more refined information. Yeah. Yeah, and this is also quite interesting research that has been done by my colleagues in BSc. So this is an AI agent that uses MCP server in order to help user to set up PhysiCell simulation. So as I said, for some cases you need to tune your PhysiCell model with some rules, with some parameters, and this can be tedious, and sometimes you need to you do not know which parts of the parameters to touch. So here is where the MCP can come to help. With just the natural language, you can prompt an AI agent that can, for you, alter and modify the simulation flow. This is a quite experimental part, and we can also try this in the hands-on as well. Yeah, and with this, I think I can conclude the presentation. So if you have any questions, it is time now. Thank you.